All right, lesson 1-8. So today we begin looking at what's called a rational function. So a rational function here, this is their keyword here. Today specifically, we're going to graph and describe key features. The main portion of today is going to be about describing key features. That's the goal for today. If you learn how to graph, great. But more importantly, I want you to know how to find the key features. That's what I'm going to focus on today. Now, what is a rational function? Well, on the next slide, it tells us a rational function is any function that can be written in this form right here. So if you go to your next slide, just go ahead and circle that up. This is a rational function. A rational function can be written as one polynomial divided by another polynomial. Now, specifically, I want you to look over my wall right above where you sign in. What is rule number 1 under domain rules? What does it say? You cannot divide by 0. That's very important right here. Underline that on your packet. G of x refers to what is doing the dividing. That's the polynomial that's doing the dividing. It cannot be 0 because in math, well, in the world, you're not allowed to divide by 0. That's undefined. So that's the keynote here. So we are still going to see curves. The graph's not going to be a line. It's going to be curved. But today, it's not going to just be smooth curves that are continuous. You're going to start seeing curves that break. Okay? So a couple more things before we get in. This next slide here has a bunch of key features, 6 of them to be specific. We have domain, something called a hole, a vertical asymptote, a horizontal asymptote, a y-intercept, and a 0. Notice we have 6 key features here. This page right here for you is a cheat sheet. I gave you this right here so that when you're at home doing your delta math and you're like, oh man, we talked about this, I forgot because it was so much new stuff I hadn't seen before. This is your cheat to have right in front of you. Have this open when you do your delta math. This is your cheat sheet. So what's this slide right here? Your cheat sheet. It'll tell you how to do everything that we go over today. Okay? So you can refer back to that. You refer back to that on your own. I'm going to be telling you how to do it as we go along, okay? And hopefully by the end of class, you'll remember quite a few of these 6 things. First, we have 2 new things we need to talk about in this slide. It's called a hole and a vertical asymptote. It was on the previous slide, key feature number 2 and key feature number 3. The hole and the vertical asymptote. A vertical asymptote occurs whenever a graph breaks, and specifically when it breaks when the 2 pieces head off towards infinities, whether positive or negative doesn't matter. Check out this graph here. Would you say this blue graph is one piece that's continuous, or would you say it's broken into 2 pieces? It's broken into 2 pieces. Now, the break occurs at that red line. What does the blue graph do as it gets closer and closer from the left and from the right? As it gets closer to this red line, what does the blue graph do? Does it point right at each other? No. They turn and they go towards what directions? Opposite infinities. They go to infinities. Because of that, a vertical asymptote is also known as an infinite discontinuity. What it means, discontinuity means break. So this describes the break. What type of break is it? It's a break that goes to infinity. So they call it infinite discontinuity. Now, if you wanted to talk about, so describing the blue graph, you would say it has an infinite discontinuity. If you were talking about the red dashed line there, you'd call that a vertical asymptote. So what's circled is describing the red dashed line. This word up here, the infinite discontinuity, is telling you how the blue graph breaks. The other type of discontinuity that comes up with rationals is over here called a removable discontinuity. This is when the graph gets an open circle. You've probably seen those in the past, but you didn't know what creates them. Today you're going to learn what creates an open circle. The open circle itself is called a hole. Removable discontinuity, that's what when describing the blue graph. So if you describe the blue graph and you said, is this one piece continuous or is it broken? You should say it's broken. What type of break does it have? The word would be removable, and you'll see why they call it removable in a second. Now, if you're saying, let's look at it, tell me about the break, then you'd say, well, the break is a hole. That's how the words come in. Now, I'm not going to be in particular on the vocabulary, but that's what it is. This middle section right here, we're not dealing with. This is from piecewise functions right here. If you want to make a note on that, this is piecewise functions that create a jump discontinuity. Okay, but we're not doing that today. We're not doing that today, so I want to stick with that. So there's your first bit of visual vocabulary there to help you out when I talk today of what's what. All right, next slide. This slide gives us the definition of a vertical asymptote. Now, there's something new with this that you probably haven't noticed before. And I want you to look at these limits. Let's just look at this limit right here. What do you see that's different about this limit than any limit we've done so far up to today?
It has the plus sign up on the.
That's right. It has a plus sign on the A. If you're like, wait, what does that mean? Well, what the plus means is that anytime you have a plus or a minus on the X, that's indicating to you that the graph is broken. I'll say it again. Anytime you see a little plus or a minus, not a negative in the front, but I'm talking about where the power is. If you see a plus like this one, you see a plus or a minus, that's indicating the graph is broken. Let's just say broken graph. That's saying the graph is broken. So what does that little plus or minus mean? It's broken. Specifically, if you have a plus, it tells you to look at the piece that's just to the right of the break. So notice our graph here. This little visual aid is the red graph on the left or the right of this break at A. You see how it's on the right? That's why it gets a plus. Whereas this one, this piece is on the left or the right. Left, and that's why it gets an A minus. Make sense? Okay, this one here, not to be confused. By the way, we could plug in a number. Someone give me a number instead of A. A is weird to be a number. What number do you think this could be? It's to the right, so how about 4? If this was the number 4 here, what it would say is 4 plus. Does that make sense? And if this was again a 4 as well, that was a 4 right there, then this would be 4 minus. So when you see the plus or minus, what should you think of when there's a plus or a minus? The graph is broken. And if you see a plus, that means you're looking at the right of the break. And a minus means the left of the break. Now, you're not looking way over here either. You're not looking way over there. You're looking just to the immediate left of the break. What's happening at the immediate left? In this graph, what's it doing just immediately to the left of 4? Is it rising, falling, getting flat, or coming to a point? Falling. That's why the answer is negative infinity there. Okay, that's a vertical asymptote. We will also see horizontal asymptotes. Okay, so last definition before we get started. A horizontal asymptote is when the graph gets flat. So up to today, on limits, every time I've asked you, hey, what's happening? Does it rise? Does it fall? Does it get flat or come to a point? Today, up to today, the only answers we've ever had is that they rise or they fall. Today, we're going to start seeing graphs that get flat. If they get flat, so what do I mean? This graph is still curving, but do you see how it's starting to flatten out? That's what it means to get flat. If it gets flat, that means we have a horizontal asymptote. So this is showing you here. Notice this does not have a plus or a minus. Why does this not have a plus or a minus? There's no break. Very good. Look at the picture. Do you see a break there? No, it's not broken. What about this one? This does not have it has a negative in front, but it does not have a plus or a minus. Why is that? There's no break. You got it. So if there's no break, you don't put the plus or the minus. All right. That right there is our vocabulary. Let's get started. So example 1. Now example 1, I've given you the graph, and what we're going to do is fill in our key information based off the graph. I want you to look at this picture here, and let's talk about it. First off, domain. Domain refers to which variables? X. We want to talk about the X values. What X values are used on this graph? For example, does this graph travel forever to the left? Yes, it does. So our graph, I go to our domain, we're going to be coming from negative infinity. And if you remember, you put a parenthesis because that means you're approaching it, but you never actually get there. Parenthesis means you approach it, but never get there. So it goes left forever. Now, does this same piece of graph go right forever? No. It approaches a break. Where's that a break that it approaches? What X value? At 0, X equals 0 here. Now, do we ever get to 0?
No.
No, we only approach it. For that reason, it's a parenthesis. Now, this graph has 2 pieces, correct? So we're going to have a union. A union means we have a second piece coming. Now, this second piece, as you look at it, does it go left forever? No. What X value does it approach? 0. So again, parenthesis 0. And then does it go right forever? Yes, it does. This one goes right forever. So how far is forever? Infinity. Again, you only approach infinity, never get there. So that would be our domain. So this is just showing us what we call a parent function. That just means the standard rational. That's what it'll look like, these C curves like this. Let's talk about the range. Range means y values, how low to how high. How low does this first piece of graph go?
For
Forever down. So what symbol means forever down?
negative.
A negative infinity. Okay, that first piece, how high does it travel? To 0. Does it get to 0? No, it only approaches it. So parentheses. Second piece, how low does the second piece go? 0. Does it get there? No, it only approaches. Okay, and how high?
Infinity.
Infinity, good. So a typical rational function, the domain and the range are from negative infinity to 0 and 0 to infinity, both of them. Okay, now tell me about this graph. The first piece, is it increasing or decreasing? Decreasing. What about the second piece? It's decreasing as well. They're both decreasing. So do I ever increase? Now put an NA here. A typical rational function does not increase. A standard one doesn't. Now we could put a negative in the front. Now it's all flipped, but typically they don't increase. But what do they always do? Decrease. Go ahead and just copy either one of those. It's going to be the exact same values. Just copy it straight down again. We typically decrease on the entire domain. Okay, now even or odd. When you look at the graph, remember, a graph is even if it perfectly reflects or has symmetry across the y-axis. Does this graph have y-axis symmetry?
No.
So it's not even. To be odd, it has to have perfect symmetry across the origin, which means if you picked any point, you remember how this works? If you picked any point, what has to be true for it to be odd? The x and the y
Negative.
have to be negatives. Is that the case here? Okay, so this function would be called a odd function. The standard, the parent function, I should say, let me use the math vocabulary. The parent function is odd. Now this graph does not have any holes. We'll be careful about this because when we get to the calculator doesn't show you a hole right away. I'll show you how to find it in a moment, but it does not have any holes. A hole is that little open circle that would look like that, but we don't have any holes on this graph. Okay, second question though, vertical asymptote. Do we have a vertical, show me with your arm, which way is vertical? Okay, do you have a vertical asymptote in this graph?
Yes.
Yes, we do. What's the equation of that vertical asymptote right there? X equals 0. You must hear me. You must on your homework and on the AP exam, doesn't matter. Put X equals. If you just put 0, it's going to count wrong all the time. This is one of the lessons that I get the most remind messages from students over in the past, is that students are saying, hey, Delta Math is counting my work wrong, and look, and they screenshot what the answer should be and their answers, and the numbers are all right. But what's the problem is the student put the answer as 0 here instead of putting X equals 0. And I just realized I would get counted off right here. I didn't close that parenthesis. There we go. Okay, do we have a horizontal asymptote?
Yeah.
Yeah, what's our equation? Y equals 0. Again, you must put that. Does this graph cross the y-axis? We do not have a y-intercept, so that point is not there. And finally, a 0. Do we cross the x-axis anywhere? Okay, so there it is. That's how the typical key features, what they'll look like on the parent function. Now here's the deal. We won't see any graphs that are exactly like the parent function. They're going to try to mix them up. But these are the standard key features. Now, when we get to example 2 here, I'm going to start showing you what happens as we complicate the graph. Now, here's the algebra. When you look at an equation, here's the algebra that occurs that creates the differences over here. First off, when you look at this equation, I have it in what's called factored form. With factored form, we can simplify this equation. Do you see anything that could cancel out when you look at these factors? The x minus 2 and the x plus 2 won't actually cancel out with each other. They're multiplying. The x plus 2 and the x plus 2, I want you to cross those out and I want you to write that this is a whole. Now, remember, x is a liar. Truthfully, what I should do to show all my work is I would put equals 0 and solve. But if it says x plus 2 is a factor, do you remember what that x will actually equal? -2. Okay, go down to whole, and for a second, I want you to do a parenthesis, because a whole is going to be a point. Put -2, comma. Leave a blank and close the parentheses. We don't know what the y value is yet, but I'm going to find that in a moment. Actually, let's just find it right now. So you see how I cut that out? Wow, why did I cross those two out?
Cancel out.
Why did they cancel out? They were identical. Factors multiply. Factors are multiplying. These are dividing. What's the relationship between multiplying and dividing? They're opposites, so you can cancel those. So because they canceled, that's what mathematically becomes a whole. The way you get your y value is you plug in the x value into the leftover equation. So this part's gone. So what I'm going to do is to find the y value, I'm going to plug it into what's left over. So in the numerator, what's left over after canceling those out? Just an x. So I'm going to replace the x with -2. You following what I'm doing? Now in the denominator, what's left over after crossing out the whole at x plus 2? X minus 2. What are we going to replace x with? A -2. So it's a -2 minus 2 more. Mathematically, what happens right there? What's -2 minus 2 more? -4. So I have -2 divided by -4. That's going to become 2 negatives become a positive. 2 goes into 4 how many times? That becomes 1/2. So my y value is 1/2. Now I want you to look over at the graph I've given you. If you go left 2 and up 1/2, you'll see that's where that open circle is located. So we got our whole. That whole is located by you cross out or simplify any factors that are opposites. Or they'll look identical, but opposites meaning they're multiplying and dividing like that. And then you plug in the value. That's how we got this whole that's right there in the picture. Okay, come back. Any factors of x that remain in the numerator become a 0. So point an arrow at this x right there. That x is going to become a 0. And if it's an x by itself, it'll be a 0 at x equals 0. So go down to your zeros and put x equals 0. And at the graph, you'll notice that's this point right there. So if this first one was the whole that we found right here, this was the whole. Let me make that more obvious in red since I kind of wrote it in red earlier. That whole occurs right there. The 0 occurs at 1. It's the leftover factor. Now, the remaining factor of x in the denominator becomes a vertical asymptote. So draw an arrow at this one. This is a vertical asymptote. If it says x minus 2 is a factor, what does x actually equal? Equals +2. So go to vertical asymptote and put x equals 2. That's what you see here on this graph. It's a vertical line at x equals 2 to represent that. Now, how you find the horizontal asymptote, I'm kind of going one at a time. Oh, sorry, let me go domain. Any value that comes from the denominator, any value of x that was ever on the denominator, that's what the domain cannot equal. Because remember, the rule is with polynomials, it's supposed to be all reals. And this is a polynomial divided by a polynomial. So you'd think it's all reals. But the thing is, you're not allowed to divide by 0. So any of these values from that would be create 0 in the denominator become a problem. And so for our domain, we're going to say x cannot equal. And you put whatever values occur on the bottom. I'm going to go numerical order, which means I'm going to put the -2 first, followed by the +2. That's what x cannot equal, but x can be all other real numbers. So x cannot equal the x value of the whole, and it cannot equal the x value of the vertical asymptote. But all other real numbers is good for the domain. These are our only breaks. Now on this range, I'm going to let you, since we did range example ago, tell me about the range. Do we hit all reals? Do I go down forever?
Yes.
Do I go up forever? No, I have a break here and I have a break here at the whole. So the range is going to have 2 breaks. It's going to be written this way. Y cannot equal What are the two values that we discovered that have a y value at a break? Look at the. It does not hit 1 and it does not hit the half from the whole. It does not hit the half from the whole, and it does not hit 1 from the horizontal asymptote. But other than that, y is all real numbers. We haven't found the horizontal asymptote. We'll get that. You can go ahead and put that in if you want. That's going to be y equals 1. The rule for that has to do with the exponents. When you look at these exponents of x, you see, are the exponents that what is the exponent if it doesn't show an exponent? Not a 0, a 1. And what is it in the denominator? 1. The rule is that the exponents are the same, you divide your coefficients. And let's just put that here. This is the acronym. Exponents are the same. You're going to divide your coefficients. That's from the rule, the cheat sheet. If you look back at the cheat sheet, that's let me go back here. Cheat sheet, where is it? This is the rule right here that I'm doing, this one. If the exponents are the same, it's going to be y equals divide your coefficients. And so that's where I am writing each DC. So if you look back at your notes, you know where to go on the cheat sheet. This becomes y equals 1 because the exponents are the same. It was a 1 and a 1, and so you divide the number in front of them. This is like a 1, this is a 1. 1 divided by 1 is 1. All right. This graph, is it increasing or decreasing? Decreasing. What about here? Decreasing. So we are not increasing. We still do not increase. We are still decreasing, and it's decreasing on the domain. So you can write the domain all over again. It's the same values that it's decreasing on. Actually, I don't think you could write decreasing that way. I think you have to use these symbols. So it would be from -infinity up until -2. And then from -2 to 2. This is crazy on this one. And then 2 to infinity. I'm going fast here. There's 3 intervals that I'm decreasing. I decrease here to the whole, but then there's a break. And then I decrease from the whole to the asymptote, and then there's a break at the asymptote. And then the last piece decreases as well. So I'm always decreasing. Those are the 3 intervals. From -infinity to the whole, from the whole to the asymptote, from the asymptote to positive infinity. Those are the 3 intervals. This function, is this even? Is it odd? Or is it neither? Pick any point. Let's just say this point right here. This point is right how many units? 4 up 2. That's 4, 2. Do I have a point at -4, +2? Do I have a point at -4, -2? No, it's neither. Finally, the y-intercept. We can see from here, what is the y-intercept? 0. The way you would get that is you plug 0 into the equation, okay? I don't think I mentioned that earlier. What you would do is you plug 0 in. And so you can do it whatever's left over. So it becomes 0 over 0 minus 2. I'm plugging it into what's left over. If you plug that in, 0 divided by -2, what's 0 divided by -2 going to equal? 0. And that's why we have a y-intercept at 0. So now that I filled out this, I'm going to show you 2b. I'm going to show you how these limits are different, okay? Now, looking at the graph that the same graph, same equations. This time I want to talk about our limits. So look at the first 2 limits, because this is how delta math is going to look. They're going to give them to you 3 limits with a function evaluated somewhere. And they're going to expect you to do this on your delta math. I want to make sure you understand it. When you see a minus and a plus, what is that telling you about the graph?
There's a break.
There's a break. We want to look at the break at -2 here. Not -2. Yes, -2. Sorry. -2. We want to look at this break. So we're not looking at the asymptote break. We're looking at the whole. So this says a limit, but you could think of as what is happening to the y values as x approaches -2 from the left side. So let me say it again. What's happening to my y's as we approach the break at -2 from the left side? Now remember, there's 4 options. It's either rising, falling, flattening, or it's coming to a point. So here I go. I'm going to take from the left side, I'm approaching my graph. So let me put a point on there so you can see what I'm doing. Like here's where my eyes are. My eyes are right there. As I move towards -2, what is happening to my graph? Am I rising, falling, getting flat, or am I approaching a point? You're approaching a point. Now, if you're approaching a point, you ask yourself, what is the value of that point? And we already found it in the previous slide. Do y'all remember what the value was? It was the y value was 1/2. Put 1/2 there. That's what happens as we come from the left. Does that make sense? This is what's happening to the y as we approach -2 from the left side. Let me say it again. What's happening to the y as we approach the break at -2 from the left? And so I went this way. Now, what would this one say? What is happening to y as x is approaching -2 from the right side? Let me say it one more time. What's happening to y as we approach the break at -2 from the right side? So here's the break. So I'm going to come from the right side. What's happening as I'm coming from the right side? Is it rising, falling, getting flat, or coming to a point as you close in on -2?
Come to one.
I'm coming to a point. If it's coming to a point, you say, what is the value of that point? 1/2. Put 1/2 there. Now, if the two values are the same, you don't have to use a plus or minus. You could just say the limit of g of x at -2 is, now are these the same? So you put 1/2. If they're the same, you don't have to do the plus and the minus. It means it's the same whether you come to left or right, doesn't matter. It doesn't matter that there's a break, the limit's the same value, so you can put 1/2. Now, different question. If it just says, what is g of 2? That would mean you plug 2 into the equation. Now look at the table just to help you out. If we plugged in 2 into the equation, what's the y value? Now I want you to say right here is, if you don't put equals g of 2, you're not supposed to, I don't think they count off in AP pre-cal, but in AP calculus they do. So I want to prepare you for that. Don't put equals undefined because you don't equal something that's undefined. You just say it is undefined. Now, the reason this is undefined is because the graph is broken. What's happening at -2? Does the graph actually exist there? No, it's broken. That's why it's a hole. That's why it is undefined itself. But does its limits exist? Yes, the limits exist. Okay. Now, let's talk about the end behavior of this graph. End behavior, if you see the words end behavior, that's talking about what's happening as you go far left and far right. Okay, so now limit as we go far to the left. Let me do my dot again. This is saying, here, let me read this limit for you. What is happening to y as x approaches -infinity? Let me say it again. What's happening to y as x approaches the far left? So what is happening? Let me move my point. As I go farther and farther left, what's happening? Is the graph rising, falling, getting flat, or coming to a point? It's getting flat. Now, if it's getting flat, you ask yourself, what's the y value it's getting flat with? Or beside? The answer is 1. I'll do this in red because it's a red asymptote. The value is 1. Now, this in behavior says what happens to y as x approaches infinity. Translation: what happens to y as x approaches the far right? What happens to y as we go to the far right? Do I rise, fall, get flat, or come to a point? You get flat. What value do you get flat with? 1. And that's how you do the end behavior of a rational function. Now, I've shown you a lot and I've gone really slow. Today, though, it's about understanding how to get the key features. So I just showed you what they all are, but I probably went so fast you didn't catch how to find. So from the rest of the class period, the rest of my examples, starting with example 3, what we're going to do is I'm going to show you mathematically how you find them and try to do it as quickly as possible. Okay? Make sense? All right, example 3. Notice this time I don't have a graph for you to cheat and look at. So this time it's a blank graph. Here's the equation, and what we're going to learn next class is how to factor, or we're going to review how to factor to get it from this form to the factored form. Truth will be told, when you are taking your test, I'm going to give you a heads up right now. You're going to be giving what's called standard form. You're going to be given it in this form, and what we'll have to do, step 1, is define the Factored form. Today, I'm doing step 1 for you. I'm gonna give you the factored form. So beginning here, what do you think we do first with this equation when you look at this equation right there?
Divide the x plus 2.
Yeah, let's cancel those out. Now, do y'all remember if they cancel out what it's called?
Oh.
A whole. This is one of the 6 key features you're gonna have to find. So the whole is gonna exist at x equals what value? -2. So for a whole, it's gonna look like a point. Do -2, comma. Now, we don't know the y value. Do y'all remember? How is it that I find the y value? Do you remember what to do? Plug in -2. Plug in what -2 to what's left over. So I'm gonna say y equals, and I'm gonna plug in -2 to what's left over. I have a -2 minus 2 over -2 minus 3. Whoops. -2 minus 3. We can simplify that. A -2 minus 2 more. -4. Parentheses are for multiplying. There's nothing to multiply with. I can drop the parenthesis. -2 minus 3. -5. And I can simplify that. A negative divided by a negative becomes a positive. It's at 4/5. So I'm going to come back over here and put in a 4/5 there. You could do a decimal. That would be 0.8. I'm going to go to the graph and plot that point. A whole is an open circle, so go left 2, up almost 1, and put an open circle. We're going to have an open circle right there. There's our whole. That is -2, comma 4/5. Okay, next. I have an unused factor of x in the numerator. What is that going to become?
0.
That's a 0. Very good. Our 0 is going to be x equals 2. X equals 2. So go 2 units to the right, put that point. There it is, 2, comma 0. We have an unused factor of x in the denominator. What's that going to be? That's a vertical asymptote. That'll be x equals 3. X equals 3. Now, show me again with your arms. What does vertical mean? Okay, so we go 3 to the right and draw that straight up and down line. 3 to the right, straight up and down line. There it is, right there. Questions over that? Okay, so now the domain. The domain is x cannot be any values that were that came from factors of the denominator. Whether they've been canceled or not, doesn't matter. Those are the undefined values. Where are we undefined? 3 and -2. I'm going to put them in order. I'm going to say x cannot be -2, comma 3. I'm going to just put them in order. But because these are made up of polynomials, though I can't be those two values, I can be every other real number. So it's all reals except for those two values. That's where that comes from. So now we have 1, 2, 3, 4 values done. Now the horizontal asymptote. What you do for this is you look at the powers. And what I do is I go back to the standard form. I know I haven't used the standard form yet. I think it's easier to see. Tell me about my exponents. Are the exponents the degree, specifically the degree, meaning the highest power? Is the highest power the same, top and bottom?
Yes.
Is it bigger on the bottom or is it bigger on the top?
Yes.
They're the same. So what I want you to do here in parentheses is just put each DC. This is for you later on if you want to check the rule. That's what your rule you're looking at. That stands for exponents are the same. The DC means you divide your coefficients. And it's this, by the way, is always a y equals. So you divide your coefficients. How many x squareds do I have in the numerator? Nope. How many in the numerator?
Oh,
1. How many do I have in the denominator? So it's 1 divided by 1. What is 1 divided by 1? Okay, let's add that to the graph. Horizontal asymptote. I should have asked you. Horizontal goes that way. Put that on there. Y equals 1. Now I can figure out what this graph looks like. I'm going to go ahead and find the y-intercept, but I can tell you what it looks like now. I know with confidence what it's going to look like. The y-intercept. The way to get the y-intercept is you plug in 0 to the equation. So I'm going to write down here f of 0. And here's the shortcut. If you look at the standard form, anything that has an x, a variable of x, will end up being a 0 and will cancel out. It'll simplify out of there. All that's going to be left is the constant divided by the constant. So I always go to this form because it's easier. It's going to be -4, the constant, divided by this constant, which is -6. So it'll be -4 divided by -6. What happens when you take a negative and divide it by another negative? Positive. And what number goes into both 4 and 6? 2. 2 goes into 4 twice and goes into 6 2/3. So wherever 2/3 is, a little over a half, that's our y-intercept. Okay. 0, 2/3. Okay, now I'm going to connect my pieces. Every graph follows an asymptote. So I know I'm going to be approaching that asymptote. So I can go from there over like this. And I'm just connecting my pieces. You all right over there? You all right? All right. Connect those pieces. Now, on the other side, here's the two options. Every graph will either reflect over across the asymptote straight across, or will reflect diagonally. Here's my question for you. Do we have any other zeros over on this side? Because I know my graph has to approach these asymptotes. I'm either going to be on the right over here, or I'm over here, because it's all reals except for these points. So I have to exist on the right. It's either in this corner or this corner. Question, do I have any other zeros listed in our problem? Because I don't have any zeros, it has to be this corner. Does that make sense how I found that out? How did I know that? Because it had no other zeros. It had to be that corner. They had to be diagonal. All right, let's finish off some limits here. I'm going to read these off, this time just one time around, and I'll have you respond back what you think. Take your guesses here. I've got a whole bunch of these examples. If you don't speak up loud, you'll be getting them wrong at the end. If you are guessing out loud, even if you're wrong on this example, I guarantee you, by the time we get to the last one, you won't be getting wrong anymore. You'll figure it out. So make sure you're talking out loud. This one says, what's happening to the y's as x goes to -infinity, meaning we go left? What happens to this graph as we go left? I'm going to do a countdown. I want you to say either rise, fall, flat, or point. Those are your four options. Rise, fall, flat, or point. What happens as we go left? 5, 4, 3, 2, 1. Not point, it's flat. As we go left, this graph goes to it gets flat. What value is it getting flat with? 1. That's going to be 1. Okay, we're going to do this again. Again, a lot of you got that one wrong. But as long as you're guessing, by the end, you'll be getting them right. Keep guessing. Okay, what happens as we go to the right? What happens as x goes to positive infinity? 5, again, rise, fall, flat, point. 5, 4, 3, 2, 1. Flat. Good. This piece right here gets flat. What value does it get flat with? 1. What's the y value, I should say? 1. Okay, this one. I see a little negative sign symbol. What is that telling me? Left. Left of a what? Left of a break. There's a break at -2. Look at the break. What happens as you come from the left to this break? Rise, fall, flat, or point. 5, 4, 3, 2, 1. Point. What's the value of the y value of that point? 4/5. You got it. You got it. Okay, this one, indicating a break here. What happens to the y's as x approaches -2 from the right side of that break? So as you come from this way towards -2, rise, fall, flat, point. 5, 4, 3, 2, 1. Point. Perfect. What's the y value of that point? 4/5. Now, this limit doesn't show you a plus or a minus. It's the same number though. So what you do is you look, are these the same or are they different? They're the same. You put 4/5. That means it does not matter whether you come from the left or the right, you're approaching 4/5. All right, next one. Whoops, way too far. This one, I see a 3 with the minus. What is the minus indicating? Left side of a break. What happens as I approach 3 from the left side, just to the left, but still going towards this break? Rise, fall, flat, point. 5, 4, 3, 2, 1. Fall is correct. What mathematical symbol means fall? Yeah, give a high five. That means it's falling right here, by the way. That's coming to the left of it. All right. What's happening to the y's as x approaches 3 from the right side of the break? 5, 4, 3, 2, 1. Rise. Good. Now, are my values the same? No. And by the way, if they're infinity, you treat it as if they're never the same. Infinities are they're never the same. So we're gonna say does not exist. Now, if you're like, wait, why are infinities not the same? Because infinity might be on one side, we might really be approaching something like a trillion. The other side might be approaching 14 trillions. Is 1 trillion the same as 14 trillions? No, it's just such a large number, we don't know. They could be different. So if it's ever an infinity, you're gonna say D and E. Oh, I didn't tell you what that stands for. That stands for, someone did their homework I saw earlier. Does not exist. That's what that means. D and E stands for does not exist. On your homework, it'll just say D and E. Make sense? All right, we're gonna reload and do it again. I'm gonna do it another time before I ask you to do it. Let's look at part B. All right, look at this equation. What do you see we could do? Take a look at the factored form here. What can we cancel out? An x plus 5 with this x plus 5? What does the squared mean?
Two.
There's two of them. So this x plus 5 would cancel with one of these two x plus 5s. Now, if this is the case, that's not going to be a whole. Here, this is not a whole. And here's why. Since a factor of x plus 5 remains. It's not a whole. So even though it canceled, that one's not a whole this time. Because you're going to call it something else. If it still remains, by the way, that's why they called it removable on the previous slide. I don't know if you remember, we had infinite discontinuity, jump discontinuity, and removable. The reason they call it removable is because you can remove it from the equation. That's why they call it removable. This still remains. It's forever there. So what type of break is this one? It's an infinite discontinuity, also known as a, over here, what word? What do you call a factor that remains in a vertical asymptote? That's a vertical asymptote at x equals what value? -5. X equals -5. We have a vertical asymptote. So we said this is not a hole. So do I have any holes? I'm gonna do NA. My domain, I just cannot be any value of x that ever came from the denominator, which means I cannot be what value? Not, yeah, there you go, -5. But what can I be? Everything else. Okay, on the top, we cancel the x plus 5. Does this 4 have an x? This is not a key feature. That's nothing. For here, I'm going to say not a key feature. Not a key feature. So for you, you're not going to do anything with the 4. All the 4 is going to do is make my C curve less like a C and a little bit more just like a, oh, I don't know how to describe it. It's just not going to make as much of a C curve. It's going to be a little bit kind of like if you pulled the two ends of if you pull them tight, if you think of a string that's set up like a C and you start to pull it tight, how it straighten out a little bit. That's what that number 4 will do. It'll straighten out the C. So that's not a key feature. So let's go to a horizontal asymptote. Look at the powers here. You look at the degrees specifically. Are my degrees the same? Are my exponents the same? Are they bigger on the bottom or are they bigger on the top? Okay, this is the first time you've seen this. Put it over here in parentheses, Bobo. What the cheat sheet would tell you if you go back to that first page, bigger on bottom, it's y equals 0. If your exponent is bigger on the bottom, it's always going to be y equals 0. Let's go ahead and start adding this to the graph. I don't know why I'm waiting so long. Here it is, y equals 0. We had a vertical at -5, 2, 3, 4, 5. Here it is at -5. So let me add those on. That's y equals 0. This is x equals -5. And so far, that's all we've gotten. Do we have any zeros up in the numerator? Any factors of x left over? No zeros. So I'm gonna do NA over here. There's no zeros, so we don't cross the x-axis. So we need to find the y-intercept. We need to find the y-intercept here. So what I do is I plug in 0 to the equation. So I'm gonna say g of 0. Now I use the standard form. Again, the reason I use the standard form is because everything that's not a constant cancels out. So these three values all cancel out when you plug in 0. So all you're left with is your constant divided by constant. It's 20 divided by 25. What is 20 divided by 25? Or what number goes into both of those? 5 does. 5 goes into 20 4 times. Yeah, good. 4/5. So you go to 4/5, put a point. So here's what I now can tell. This equation has to come from this asymptote through this point, whoops, on this way. It has to be like that. Now, I can't really tell, is it over here or over there, because my asymptote doesn't cross. So what you'd have to do is pick a point and find out if it's positive or negative. So I'm gonna do this really, really briefly. Okay, I don't want to lose yet because I don't even know if you'll ever be tested on this. But here's what you do. You pick a number that's smaller than -5. So y'all want to use -10? Sure. Take -10 and plug it in down here and see if you get a positive value or a negative value. That'll let you know if it's positive, it goes above the x-axis. If it's negative, it goes below. I'm just picking a number to the left to figure out am I above or below. If I plugged in, I'm going to use this simplified, it'll be easier. If I plugged in -10, I would have, so I'm looking at what happens at -10. Where would the point be at -10? That's what I'm doing. If I plug in a -10, it would be 4 divided by -10 plus 5. Are you tracking with what I'm doing now? Is that going to be a positive number or a negative number? What's -10 plus 5? It's -5. So is 4 divided by -5 a positive or negative number? Negative number. So at -10, we're at -5. That means this piece comes from over here. Make sense how I just figured that out? How did I just figure that out? Plug in a number to find out if it's positive or negative. Since it was negative, it has to be down there. Now I can do my limits. All right, here we go. Y'all ready to do the guessing game again? Let's see how you do. The limit of g of x as x approaches -infinity, meaning what's happening to the y's as x goes far left. Rise, fall, flat, come to a point. What do you think? 5, 4, 3, 2, 1. Flat. It's flat as you go far left. What number, what y value am I flat with? 0 this time. Okay. What's happening to y as x approaches infinity? What's happening to y as x goes far right? Rise, fall, flat, point. 5, 4, 3, 2, 1. Flat. Good. What value? Y'all are getting out. Y'all are catching on. You're getting it. Okay, how about this? When you see a -5 with that little minus in the power, what is that minus indicating? There's a break, and we're talking about the left side of the break. What's happening on the left side of this break? Is my graph rising, falling, flat, point? 5, 4, 3, 2, 1. I only heard one voice. Fall. It is falling. What's the symbol for falling? -infinity. Yep. Let me get this like that, a little bit closer to my asymptotes. Okay. What's happening to the y's as x approaches -5 from the right side of the break? From the right side of the break, what's happening? 5, 4, 3, 2, 1. Answer is it's rising. And remember, you're always the arrow is indicating you're moving towards that x value. So I'm on the right side, but I have to move towards -5. So I'm actually moving on the graph to the left, and it does rise. Okay, and last one. What would you put for this? D and E. Good. Why D and E? Anytime they don't match, or if it's an infinity, it's automatically D and E. All right, great. We have one more. Now, as we take a look at part C, I've given you a little bit of information here that we'll focus on in 2 lessons, but specifically, let's come back up here and do what I have already showed you today. What would you do first when you look at this equation here? Can I cancel anything out in the factored form? Wrong, I can. Look again. There's something. An X, Dale, good. This has an X that's multiplying. What is this 2 doing to this X? And what's that X doing in the parentheses? So do I have a multiplying X that's being divided by multiplying X? Yes, I do. Those are opposites. You can cancel those. If you can cancel something, what does it become? That's a whole. X equals what value if it just is an X? Not 1. That would be X minus 1 as a factor if it were 1. If it's just an X on its own, 0. There it is, 0. So we have a whole at 0. Let's go ahead and find the Y value. Do y'all remember how to find the Y value? Because right now we don't know it. Plug in 0 into the rest of the equation. So it would be Y equals, does anything else cancel out? Okay, just want to make sure I'm not going too fast. It would be 0 minus 4 times 0 plus 1 over 0 plus 2. What is 0 minus 4? -4. So it's -4 times 1, which is just -4 over 2. What does that simplify to become? -2. Very good. -2. That's going to be a -2. So 0, -2. Go down 2 units and do an open circle right there. There's my whole. That is 0, -2. Which, by the way, means we're not going to have a y-intercept. You know how I know that? Because is that an open circle or a closed circle? Open. And you can't have 2 points on the same x value. Otherwise, it's not a function. So we don't have a y-intercept this time. All right, pick back up. What do you call something? There's 2 on the top. 2 factors of x that remain. What do you call those? No, not on the top. These are the zeros. So we have 2 zeros. We have zeros at, what 0 is this? 4 and -1. Now when I recopy it, I want to put it in numerical order. So I'm going to say -1, comma 4. Not that that really matters, but I'm going to do it that way anyway. So if I go left 1, on a point, this is a 0. -1, 0. If I go right 4, 1, 2, 3, 4, that's a 0 right there. 4, comma 0. What do I call a remaining factor in the denominator? That's a vertical asymptote at x equals -2. X equals -2. So this will be a dashed line, a vertical. Show me vertical with your arm. Up and down. So go to -2. Add that in there.
Say oblique asymptote and I say vertical.
All right, to finish this up, what are the values of domain where the graph will be undefined? What are the only places that this graph will not exist? -2 is one of them. And 0. By the way, this green is nothing. The green. I click green. This 2 is nothing. Why is that nothing? Because it's not in parentheses with an X. That's going to be nothing. That's not going to have no effect at all. So you can, that 2 by itself doesn't do anything. But my domain will be all reals except for any factors that were ever in the denominator, any factors of x. So 0 and a -2. But I can be all other real values. So now I can connect my graph. I know my graph has to follow these asymptotes and connect these points. So since the graph has to follow asymptotes, that's the rule. This one, I can predict what's happening on the left side. What do I mean? Do we have any zeros on the left side? So I know I'm not straight across this time. I'm not straight across because I would have to have a 0. So I must be in between these 2 asymptotes on the left this way. So add in that piece and you've got your graph. Now, just make sure you caught how I did that. You could plug in a number. But how I did that is I knew I didn't have any other zeros. There was nothing mathematically to give me a zero, so I had to go diagonal rather than across. Now let's find our limits. Let's see if you can call them out to me. This limit right here, what happens to y as x approaches negative infinity? What do you think? 5, 4, 3, 2, 1. Falls. Very good. It's this one. As you go left, it doesn't go flat this time. It falls. Negative infinity. All right. What happens to y as we go to the right? What happens to y as this graph goes to the right? 5, 4, 3, 2, 1. This one rises. It rises. Okay. What happens to y as x approaches the break at -2 from the left side? The left side of the break at -2. 5, 4, 3, 2, 1. It's right here. What happened on the left side of -2? I didn't hear very many answers there.
Fall.
It falls. Negative infinity. Okay. So what happens to y as x approaches the right side of the break at -2? So here's -2. As this graph approaches the right side of that break, what happens to it? 5, 4, 3, 2, 1.
Right.
Okay, what would you say about the overall limit? Does not exist. Anytime you have an infinity or anytime they're different nut values, does not exist. Okay, what about 0? What happens to y? Oh man. What happens to y as we approach the break at 0 from the left side? 5, 4, 3, 2, 1. It doesn't fall. Rise, fall, flat, or come to a point. Comes to a point. What's the value, the y value at that point? -2. A -2 is this value here. Now, what happens as we approach it from the right? Do I rise, fall, flat, come to a point? Come to a point. What's the y value at that point? What would you say about the overall limit at 0? Okay, and now I want to give you the rule. If you have a hole, your values will be the same all the way across. Look at this. You see how they're the same all the way across? But if you have a vertical asymptote, it will not exist in the end. This is always true. If you have a hole, it'll be all the way across the same. If you have a vertical asymptote, they will change. Let's go back and you can just tell me real quick without even looking at the picture. You can just look at the limits and tell me which one came from what. If I went back to B, what would you tell me if you looked at and you saw these limits? This did not come from a hole. This came from a vertical asymptote because I have infinities. And it does not exist. Vertical asymptotes always create infinite discontinuities, so they go to infinities. What about part A? The first one. What could you tell me about this first one? What is this?
Fall.
That's a hole. This came from the hole. What about this one? That came from the vertical asymptote. You got it. All right. If you want to know the math for an oblique asymptote, what you do is you do long division. I don't want to take our time here. So just as a reminder, what you do is you take this leading term and you divide it by this leading term. How many times can 2x squared go into x cubed? Well, it goes in half x times. And so you would multiply here. And so 2x squared times a half x would become x cubed. And then you would multiply this by half x. What's 4x times half x? What's half of 4? 2, and x times x is x squared. So now what you do is, if you remember, you change your signs. You change your signs, those switch. That cancels out. This becomes negative 5x squared, and you bring down this next term. Again, this is what 3 lessons from now is all about. And then you would do it again. You would do leading term divided by leading term. Negative 5x cubed divided by 2x squared is going to be negative 5 halves. The x squareds cancel out. It's just going to be a negative 5 halves. And I'm going to stop. I don't have to go any further because the rest will be a remainder, and we don't care about the remainder. This becomes our oblique asymptote. So that's where I got this oblique asymptote right here. That's how I got that. But that's what 2 lessons is from. That's where that value came from. That's how you do that. As you do a division. I did long division here. That's how you do that. Okay. Let's look at one more before I give you some to try here. Part D. How do you start off? You guide me through this. You've seen me do this now a number of times. See if anything crosses out. Does anything cross out?
Yes, X plus five.
What do you call something that crosses out? That is a hole. Good. That'll be at what X value? -5. So for a hole though, we need a Y value. How do you get the Y value? You plug in 5 to the remaining stuff. So to the remaining equation, let me be more specific than stuff. I have a 3, I have a 2, -5 minus 4, and a -5 plus 2. Okay, let's simplify. 3 times, what's -5 minus 4 more? -9 over 2 times -3. Okay, I can cross out the 3's or make them 1's. They simplify. 3 divided by -3 would be -1. So this becomes -9. That's a 1 there. -9 divided by -2. What happens with two negatives? Become positive. I'm running out of space. I'm just going to write it right in. 9/2. That's 4.5. So go left 5, up 4.5. Left 5, 1, 2, 3, 4, 5, up 4.5. 1, 2, 3, 4.5. There's your open circle. There's my hole. Okay, let's go back. What do I do with this 3? What do I do with this 2? They're nothing. Not a key feature anyways. Just going to change the width of my graph. Okay, what about the x minus 4? That's something. That's an x. That is a 0. Well done. That is a 0. So the 0 will be at x equals 4. 1, 2, 3, 4. I'll put that on there. 4, 0. We have a 0. X equals 4 to keep this neat. What do I do with this last little piece right there? That's a vertical asymptote. If it says x plus 2, it's actually x equals -2. X equals -2. X equals -2. That's vertical means up and down. There we go. Put that on there. X equals -2. All right, we labeled that all pretty good. Domain, what are the values of x that we cannot equal?
Every number except -5 and 8.
Yeah, everything but these two values. To keep it in numerical order, I'll do -5 first, then -2. Not that that matters, but I just do it that way anyways. All values except for -2 and -5. All values except for -5 and -2. All right, horizontal asymptote. I go to the start. I think it's easier. Looking at the standard form. And you talk about the degree, but I'm going to say exponents, but I'm specifically talking about just the highest power. Are the exponents the same? Is it bigger on the bottom or is it bigger on top?
It's the same, right?
It's the same. BO, BO. And I didn't put the rule in the last one. If you want to go back, the last one would be the rule Botten. Oh, it's the same. I'm sorry. Exponents are the same, divide coefficients. So the equation is going to be y equals, and you divide the coefficients in front of the squareds. You see how it's a 3 and a 2? This one's going to be 3/2. So to go to a y value, 3/2 is the same thing as 1.5. Put that asymptote on there at 1.5. I can see how the pieces are going to look now, because I have pieces on both sides. Let's find the y-intercept. How do we find a y-intercept? Don't remember what to do? You plug in 0. You plug in 0 to your equation. So I'm going to do k of 0 here. What's going to happen is anything with an x, look at the standard form, makes it easier. Anything with an x cancels out. All you're left with are your constants. It's -60 divided by +20. What will that simplify to become? -3. So we go 1, 2, 3, there it is. 0, -3. Now we can connect our pieces of graph. Again, they always follow an asymptote. That's kind of the point of an asymptote, is it shows you what the graph is approaching. This piece, since I have a hole up here, it's got to be going this way. Whereas these asymptotes C-curve it along both ways like that. That's what my graph would look like. I don't want to forget, I'm going to go back and add in, this one was Botten, the oblique asymptote. This was the rule Botten. Put that on your notes so you can go back and look at it later. That's Botten. It was bigger on the top. Okay, back over. What's happening to this graph as we go left? Does it rise, fall, get flat, or stop at a point? What happens as we go left forever? X approach negative infinity. Rise, fall, flat, come to a point. 5, 4, 3, 2, 1. Flat. What does it get flat with? Not 3, not -3, I'm sorry. What's the y value? 3/2. That's it. 3/2. Y value is 3/2. Put that right there. Okay. What happens as this graph goes right forever? Rise, fall, flat, or to a point. 5, 4, 3, 2, 1. Flat. It's approaching this asymptote, which is at 3/2. Okay. I have a -2 this time with a minus. That means it's a break. What happens to the y's as x approaches the left side of the break at -2? So here's -2. So I'm approaching the left side. The break on the left side. What happens? 5, 4, 3, 2, 1. It rises. What happens as I approach -2 from the right side? 5, 4, 3, 2, 1. It falls. Very good. What is this going to be? D and E. That means this must be a vertical asymptote or a hole. This came from a vertical asymptote. You're right. All right, now let's look at -5 from the left. -5 from the left. What am I doing here? Rising, falling, flat, or coming to a point? 5, 4, 3, 2, 1.
Come to point.
Point. What's the value of that point? The y value of that point? 9/2. What happens as I approach it from the right side? Rise, fall, flat, coming to a point. What's the y value of that point? 9/2. Are these values the same?
Yeah.
What can you tell me about that break that must be true just by looking at the limits? It came from a hole. That's a hole. Wow. I'll tell you what, you did some work there. There's one more. I think this one could be a DOL. I think you've seen me do enough. It's time for you to practice one. All right, now after completing that, let's come over here. And now let's finish with example 4. It says a rare species of insects was discovered in the Amazon rainforest. To protect the species from extinction, entomologists, I don't know how you say that word, transferred a certain number of insects to a protected area. The population P of a new colony T days after the transfer is given by P of T there. Find the y-intercept. All right, so this is the way it's going to happen on your exam. Is you're going to have a real problem, and it's going to test you on one key feature, just one. So you have to remember how to find it. In particular, part A, it says find the y-intercept. How do we find the y-intercept? Plug in 0. If you remember that, you can get the value here. So we plug in 0. So P of 0 is what we're plugging in. Would equal 50 plus 25. Well, I got really crammed there. Let's try that again. 50 plus 25 times 0 over 2 plus 0.01 times 0. Now, you might remember, though, I said there's a shortcut. Anytime you're finding the y-intercept, what will always cancel out? Everything other than the constants. What's the only constant in the numerator? 50. What's the only constant in the denominator? 2. It's going to be 50/2, which is, what is that? 25. So in context of the problem, what does P, this is the P value, the T is 0. What does P of 25 mean? Is that 25 days?
The population.
That's the population. P is the population. So population what? Yeah, there are 25 insects on day 0. That's the explanation. Maybe I should say there is a population since P was a population. There is a population of 25 insects on day 0. That's the translation. It says interpret this value. That's the interpretation. You explain what 25 is. You explain what the 0 is. Does that make sense? Okay, next. Find the limit P of T and interpret your answer. Okay, so what do you think happens as we get really, really large here? Well, I don't know, but we could plug in a number to find out. What do y'all want to say is a really large number? I mean, we could go through we could go through the process. We'd have to factor this. Here's what I know is this graph. Tell me about my exponent rules. Is my exponent here bigger on the top, bigger on the bottom, or the exponent's the same? The same. So the rule here for the horizontal, that's in behavior. In behavior has to do with the horizontal or oblique asymptotes, is you divide your exponents. So, excuse me, divide your coefficients. This is each DC. So this problem is each DC. Your exponents are the same, you divide your coefficients. So really what you're doing is y equals 25 over 0.1. 0.01. That's going to be my intercept. Now, do y'all know what that is or what you do when you're dividing by a decimal like that? You move, if you have to move the decimal 2 times the right, you have to add 2 zeros. So the value is actually going to be 2,500. Here's what it means on the graph. We're going to have a horizontal asymptote way up at 2,500. Now, I don't know what the graph is doing on the left, and honestly, I don't care. What I do know is this. Either the graph is going to approach it this way from the right, or it's going to approach it this way from underneath. Do you follow me? My guess is because it's population, it's probably this dashed line. That would make sense to me. It's coming from 25. Actually, we could state with confidence. Well, we know what the y-intercept is. Where's the y-intercept? 25. So the graph has to be approaching it from this way. So what is the limit as we go to the right? What's happening? Is it rising, falling, getting flat, or coming to a point? It's getting flat. What's it getting flat with? 2,500. That's where it's going. So that would be my limit. So as time goes on, the interpretation is this. As time increases without bound, as time increases without bound, the population approaches is the word. Approaches 2,500 insects. That is your, that's how you would write that. That's your interpretation. Whoops, sorry. As time increases without bound means going to infinity. That's the English way of saying that. As time increases without bound, the population approaches 25,000. Approaching means that's where it's going. 2,500 insects. All right. With that, we made it to the end. You have, it's basically, it looks like a whole bunch of numbers. It's actually a DOL of the same problem with all the little pieces. So it's going to first give you the equation. It's going to ask you to find the end behavior. It's going to ask you to find some values at the table you get from your graph. Your 0. Where is it undefined? What's happening? That's the limit. What's happening means a limit. And you'll fill those out. Again, limit, what is happening? That's talking about the limits. And you're just going through those. All of that breaks down the different ways they could test you. If you want to see their particular test questions, go here, log in, go to 1-8, and you can see how AP College Board, some questions that they have from what we covered today.